I mentioned on the board here that wildcard masks at first kind of look like network masks or subnet masks. I think they actually look more like Bizarro World masks because they look totally different, actually the opposite of what you would expect a mask to look like at this point, because you've seen network masks, you've seen subnet masks. We haven't worked with wildcard masks yet. What a wildcard mask is, though, really is just a mirror image of these mask types. And I'm going to show you a way to write this out. We're going to see exactly what's going on with wildcard masking, but there is a very quick way that with practice you get even quicker with it that'll help you determine the right wildcard mask to use for your situation. And I'll show you that in this video as well. But when we use wildcard masks use zeros and ones in this fashion. The zeros are the I care bits, bits that have to match in order for an ACL to take effect. Ones are I don't care bits, bits that do not have to match at all in order for the ACL line to be considered a match. Now, this is the kind of thing that when you read it in text or even you're just looking at that and I'm telling you about it and you're like, well, okay. Once you see it in action, the light bulb will come on and you'll see actually how very simple it can be. Now, what we're going to do is walk through an example here. And if you've seen ACLs before and wildcard masks before, you can likely do this one in your head. But we're going to write it out anyway. We need an ACL that's going to allow packets sourced from 196.17.100/24, and we're going to let that enter a router's fast Ethernet interface. Packets sourced from all other addresses should be prohibited. So we're not worrying about the application of the ACL yet. We're doing plenty of that later. But what we want to concentrate right now is getting the wildcard mask right. Well, this one's a little easier because it ends evenly. 8, 16, 24, it ends at the end of an octet. So we need an ACL that allows packets to enter if the source IP address matches the first 3 octets exactly 196.17.100, and then after that, we don't care. So we're not even going to write out the entire ACL right now. Again, we got plenty of that coming. I just want to get the wildcard mask right. And here's the way you would do that. The first 3 octets we know all the bits have to match. The last octet we don't care because that mask that we were given, the network mask, the subnet mask, /24. So instead of all ones for the first 3 octets and all zeros for the last octet, as a /24 mask would be, with our wildcard mask, we just turn the ones to the zeros and the zeros to ones. That's all you got to do. So here, all bits must match. The first 3 octets are going to be all zeros. And in the 4th octet, we do not care. So those are all ones. So when we turn this, when we convert it back to dotted decimal, we know what that's going to look like. It's going to be 000255 because the last octet is all ones. And the first time you look at that, you're thinking that cannot possibly be right, but it is because you're just used to network masks and subnet masks by this point. It looks odd at first, but you'll get used to it. Now you want to watch that on the exam because if you're asked, say, for a wildcard mask, what wildcard mask, cares about the first 3 octets but doesn't care about the 4th one. Well, if I were writing a practice exam like that, I would make sure one of the choices was 255, 255, 255, 0, which is a network mask, because they're going to make sure that you understand what a wildcard mask is. And again, a wildcard mask is zeros for the I care bits, ones for the I don't care bits. That's all there is to wildcard masking. We've got plenty of it coming up in our lab, so we're going to get a lot of practice with it. If this is the first time you've seen it, you're a little fuzzy on it, that's perfectly fine. It's normal for when you start learning anything for the first time. We're going to get ahead of ourselves just a little bit here with a routing protocol and get some extra wildcard mask practice while we are at it. One challenge that RIP presents that we can work around with the IGRP and OSPF is when you have interfaces on the same major network number on a router, but you don't want to run a routing protocol on all of those interfaces. And I'll show you an example here. You're seeing the example. I don't have the addresses for you here. But what's common is that maybe we want to run OSPF on a serial interface, but we don't want to run it on the fast Ethernet interface. Well, that's perfectly fine until you look at these addresses and you say, okay, these are subnets of the same major network number, 172.12.0.0. If we were running RIP here, we'd have a little bit of a problem because RIP doesn't allow you to enter wildcard masks or subnets or anything. It just, with the network command, remember that, it would just be network 172.12.0.0, and then all of a sudden you got RIP running on your serial interface and your fast Ethernet interface, and you didn't want to do that here. So what wildcard masks allow us to do is really tie down which interfaces on a router will be running a routing protocol and which ones will not be. So here, notice we've got a subnet mask of /28. And if we write that one out as a wildcard mask, we invert it. We change the ones to zeros and the zeros to ones. That means that we have all zeros for the first 24 bits, so that's nice and even. But that fourth octet, the first 4 bits must match. So you've got 28, instead of the subnet mask has 28 ones and 4 zeros at the end. We invert that, if you will, for the wildcard mask. We have 28 zeros at the beginning and 4 ones at the end. And then you just convert this to dotted decimal. And there's your wildcard mask. So your wildcard mask here would be 00015. Because when you add up those 4 bits at the very end, that's the 8, 4, the 2, and the 1. And with plenty of practice, you'll know that by looking at it. Then you know this wildcard mask would be 00015. And again, I kind of got ahead a little bit there about making the entire process faster, because I don't want you to think that you're going to have to write this out on exam day for anything with a wildcard mask. Because frankly, you're going to get so much practice at it, there he goes again, and you're going to be so good at it, it's going to be second nature to you. And again, to make the entire process faster, just take that network or the subnet mask that you're given and just invert it. And that gives you the wildcard mask. They gave us /28. We know what that is without writing it out. We know that's 28 ones followed by 4 zeros. If you invert that, change the zeros to ones and the ones to zeros, then what you have is 28 zeros at the beginning and 4 ones at the end. And again, with practice, you'll know that when you have a /28 mask, change it to a wildcard mask, the result is going to be 00015. You won't have to do all that writing out. So again, if they gave us a /30 for the subnet mask and we needed to come up with a wildcard mask for our ACL, what would a /30 be? I'm not even putting it on the board. I'm just pulling this one out of the sky. If you got a /30 subnet mask, we know that's 30 ones followed by 2 zeros. You invert that, gives you 30 zeros, 2 ones at the end, and it would be 0003. So again, a skill that gets a little tricky to you at first, you'll be doing it in seconds on exam day. And that's going to really, really, really help you pass the exam. Coming up next, we're going to get into some lab work here and going to tool around a little bit on some live routers so we can see some ranges, because we had a couple different ranges we got to know, and of course how standard ACLs and extended ACLs are working in a similar fashion and how they work differently, and that is coming up next.